Okay, good evening everyone. Welcome to your 11th discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, Research Scholar from Department of Applied Mechanics and Biomedical Engineering from IIT Madras, and today we will be discussing about one more strengthening mechanism, that is strain hardening, followed by a discussion on how exactly do these mechanisms manifest, all these strengthening mechanisms manifest in dislocation, essentially understanding how dislocation interactions works, and finally talking a bit about strain aging and moving on to problems. Okay, so let's begin with today's topic, strain hardening. Okay, so till now we have discussed 4 different mechanisms, right? First one being precipitate strengthening, where we saw precipitates actually getting involved in strengthening, precipitates blocking the motion of dislocations and in turn affecting the total hardening or strengthening behavior in a material system. Then we saw how dispersion strengthening works, and which is kind of similar to what precipitate strengthening is, but dispersed phases are like kind of different phases compared to precipitate. Precipitates are like part of the alloy system itself, the matrix itself, but dispersoids are like separate particles which are introduced. Then we saw how solid solution strengthening works, so where solutes are actually acting as a strengthening mechanism, blocking the dislocation motion and then leading to the strengthening. And finally, we saw how grain boundary strengthening works. Right? In strain hardening, the effect is very different. Right? Here, we do not look at some other defect to actually help us in strengthening or blocking the motion of dislocation. Here, we are seeing how dislocation by itself is blocking its own motion. Okay, so for instance, essentially what is happening in strain hardening is we are inducing some strain in the material, and these strains will cause dislocation to generate. And once these dislocations are generated, these dislocations will interact with each other and in effect like block each other and cause an increase in the strength. Okay, so let's write that down. If we induce strains in a material, these strains causes dislocation generation. Okay, these strains will cause dislocation generation. Okay. Now these dislocations will interact with each other and block the motions. These dislocations interact with each other and block or restrict the movement of other dislocations. Okay? And restrict dislocation motion or motion of dislocations. Leading to strengthening. Right? So this is strain hardening essentially. So now let's understand how this strain hardening works. Okay, let's start with single crystal. How does strain hardening work in single crystal deformation? Single crystal deformation. how exactly would we characterize? So let's first draw this, okay, in some way or form. Let's say that we have a single crystal which looks something like this. This is some single crystal, and then like we are applying like strains on both the sides. Okay, some sigma stress which causes some strain. Okay, now this single crystal will have multiple slip systems, right? As you have studied that there could exist multiple slip systems within one crystal. So we can say that there could be like slip systems in this direction, another set of slip system which will be in this direction, another set of slip system which could be in this direction, so on and so forth. So there could be multiple slip systems present within a particular crystal, right? We have studied that how different angle and geometry will influence different slip systems, right? So that is something first we'll note down. Multiple slip systems. So what will happen if there are multiple slip systems and we are straining the material or applying stress on the material? If there are multiple slip systems and we keep applying load or strain or stress on the material, what will happen? There will exist a point at which some slip system, some one particular slip system will reach its critical value, right? And usually this slip system is the one which is oriented at 45 degrees, right? Because that's the one which has the highest value of Schmidt factor and therefore the lowest value of CRSS. So basically that will reach its CRSS, right? We'll reach the CRSS for that particular slip plane. Okay. So as load increases, resolved shear stress on one of the plane reaches the critical value. Resolved shear stress on one of the planes reaches the critical value. Right? So now what happens? Once one of the resolved shear stresses has reached the critical values, then dislocation will start to move in that particular slip plane, right? So dislocation will start to move. Dislocation starts to okay. So dislocation has now started to move in that particular slip plane. Okay. So it has reached, dislocation gets generated, it has started to move. Now what will happen? The load will keep increasing. Over time, CRSS on other slip systems will also get reached. Right? So other slip planes will also get activated. Other slip systems will also get activated. So now what will happen? Now these dislocations which are now newly generated will start interacting with the dislocations which were generated previously in the other slip plane, right? In the other slip system. So they will start interacting with each other. Now this interaction will lead to them restricting each other's motion and then lead to strengthening. Okay. Dislocations interact with each other and finally lead to strengthening because of what we have explained before. Okay. So this is how exactly, like in single crystals, you will see dislocations interacting with other things. Now, how does this happen? Like, what are the steps that it follows? So there are three essential steps in a single crystal system. Okay, there are three steps that you will see when this dislocation interaction happens or strain hardening process. You will see three steps. Okay? So let's first draw the graph. Okay, it will look something like this. If you draw tau versus lambda, you will get something like this. First, you will see a region where it is straight, then a sudden increase or sudden rise, a region where it suddenly rises, and then again flattens. Okay, so if we divide this, let's use a different thing. This is my stage 1, this is my stage 2 and stage 3. So we have 3 stages. Okay, so let's understand each stage one by one. So what is exactly happening at each stage? Okay, so in the first stage we will have easy glide. Stage 1 is easy glide. It's called easy glide. Okay, so in this what happens? The very first step happens. The slip system with the lowest CRSS will get activated, and it will lead to negligible strain hardening, as only like the lower CRSS slip systems will get activated. Okay, so essentially only those particular slip systems will get activated, and strain hardening will be very minimal. It will be more like dislocation starts moving, so the glide will happen. Okay, so easy glide will happen essentially. So let's write down. Slip system with lowest CRSS gets activated. That is, lowest CRSS would mean that it has the highest mid factor, right? The slip system with the lowest CRSS or highest mid factor would get activated. Okay, so we'll see negligible strain hardening. So in this stage, we'll see very negligible strain hardening. As why are we seeing only negligible strain hardening? As all the dislocation will move away from each other. They move away from each other, or there's minimal interactions. Okay, so this is easy glide, first step. So next step, where we'll see sudden rise in the strength, is strain hardening. So this is the major step. So in strain hardening step, now more than one slip systems will become active. Okay, so once that happens, dislocations will start to interact with each other, and you will see almost a linear strain hardening behavior. Okay, so essentially what is happening is pile up of dislocations will happen. They will start interacting with each other, and they will tangle. Okay, they will tangle with each other and form some sort of a cell structure. Okay, so this will lead to strain hardening behavior. So that's why this stage is known as strain hardening. Okay, so let's write down one by one. More than one slip system becomes active. Okay, so dislocations interact with each other. So once dislocations start interacting with each other, what will happen? You will see strain hardening. Okay, and the strain hardening that we will see is more like a linear. So you'll see a linear strain hardening behavior. So almost linear strain hardening almost linear strain hardening behavior is observed. Okay. And what is the main mechanism behind this strain hardening here in this step? It is just pile up of dislocation. Pile up. Okay. And finally, what will happen? The dislocation will tangle with each other, right? And forms a cell kind of structure. Okay. Okay, I think now we are back. Let me just see. Camera is active properly. Yeah. Okay. Yeah. So yeah. So what happens in dynamic recovery then? So it is characterized by a decreasing rate of strain hardening. Okay. So then now the strain hardening rate will start decreasing, and cross slip will take over. Okay. Over pile up, now cross slip will take over, and that will release all that stresses that were accumulated due to pile up. Okay. So essentially, this stage is known as dynamic recovery. Okay. So here, this is characterized by decreasing rate of strain hardening. By decreasing rate of strain hardening. Okay. So essentially, once the strain hardening rate will decrease, you will see a dynamic kind of recovery happening, and this will lead to cross slip also starting. Cross slip starts. Cross slip starts. To cross slip starts. Okay, or cross slip starts to take place. To take place. And releases stress due to pile. Okay. So now the behavior is temperature dependent in this stage, which implies that climb is also active in this stage. Okay, because it is temperature dependent, climb will also be active in this stage. Okay, since the behavior is temperature dependent, okay, in this stage, since the behavior is temperature dependent in this stage, therefore climb is also active in this stage. Climb is also active. Okay, and the intersection of dislocations is the chief hardening mechanisms. Okay, intersection of dislocations is the chief hardening mechanism. Okay. So this is what happens in a single crystal system. You will see three stages. Okay, easy glide followed by strain hardening and then dynamic recovery. And therefore, these three stages signify what are the or in what way the strain hardening will take place in a single crystal system. Okay. So what will happen then in a polycrystalline material system? So let's understand that. Deformation in a polycrystalline material. Okay. So in polycrystalline material, essentially you will see only stage 2 and stage 3. Okay. So if you look at the graph for polycrystalline material, it will look something like this. You see only stage 2 and then stage 3. Okay. Stress versus strain graph. So if I am dividing this, so there will be only stage 2 and stage 3. Can you think of why there will be no stage 1 here? What could be the possible reason why stage 1 is not present? Now think of a material system, right? Let's say you take a material like this, which is polycrystalline. What is happening here? Essentially, you will have multiple crystals or multiple grains, right? You have something like this. So you have multiple grains, right? Now, if one grain, let's say this grain, let me use a different thing. Okay, if this grain is active, okay, and then I'm looking at another grain around it. Let's say this grain. Okay, I'm seeing 1 and 2. Now what is happening here? If one set of plane deforms in one particular way, another set of grains will deform in another way, right? Because if CRSS gets active in one particular plane, in another plane the CRSS will be active in a different direction, right? So this is the major problem, because if CRSS are active in different directions, what essentially will happen? If they are all moving separately, they are not moving together, then there will be some discontinuity and which will result in the formation of some voids, right, in between. But we want a continuous or continuous system. We want it to be contiguous, right? So essentially for that to happen, they have to deform together, right? And if they are deforming together, then one CRSS cannot get activated while other CRSS are not activated at the same time, right? So essentially, the CRSS and strain hardening CRSS activation and strain hardening will take place together. So directly we'll go to stage 2, and there'll be no stage 1 in between. Okay. So let's write down. So here only stage 2 and stage 3 are observed. Only stage 2 and 3 are observed. Right. So why this is the case? Because only one set of planes cannot deform. Only one set of planes cannot deform. As this will lead to discontinuity and voids. one more important point that we can talk about in this in the deformation and polycrystalline material is that there's a minimum number of independent slip systems which are required to maintain continuity. Okay. Minimum number of minimum number of independent slip system. Minimum independent slip systems. Required to maintain continuity. That is given by, for 2D it is 2, for 3D it is 5. Okay. So this is how the deformation or strain hardening will take place in polycrystalline and single crystal materials. Okay. Now let's look at another important factor which influences this hardening, or how do we quantify this hardening essentially. Now let's look at that. So let's look at a concept known as Taylor hardening. So this gives us a means to quantify this hardening behavior. Okay. So if we look at two dislocations, what we have studied till now, if there are two dislocations present which are at say some x distance from each other and y distance each from each other in the x and y plane, then we can plot their force as a force versus y as, or force versus x as so this is force versus x as a function of y, as a function of y. Okay. So how does it look? Looks like this. On the other side also it will be similar. Right? This is how it looks. So we'll have like 1y, so this will be y, this will be minus y, then 2y, minus 2y, 2y, and so on and so forth. And here it will be 0. Essentially, what we'll have is, so let me just, essentially what we'll have is the point where it is maximum, the point where f is maximum is here, right here or here, the 2 points I've shaded. So this is at x is equal to 0.414y, and this is something that is essential for us to actually derive the hardening expression. So now let's come back to f, right? So what is the relation for f? F is equal to tau times Burgers vector, right? Tau into b. or GB by 2 pi times 1 minus mu, sorry, 1 minute, 1 minus mu times B into X. Okay, let's keep the X outside. X times X square minus Y square divided by X square plus Y square the whole square. Correct? So now if I substitute X is equal to 0.414Y and I rearrange, I will get this tau critical, the critical value of stress, to be equal to GB by 8 pi times 1 minus mu into 1 by Y. So this is my tau critical. Okay. Now let's assume that we have a structured way in which these dislocations are arranged in some material system. Okay, so let's say that we have dislocation something like this. Okay, then we have something like, and then again like this 3, then again like this. Okay, so this is how the dislocations are arranged. Like we are saying it's in a structured way these dislocations are arranged. We are saying the distance in both x and y direction that we are seeing here are h. Okay, so now if I look at one particular region in this, let's say I look at this region. This region, okay. Here, this is 2h, okay, and this is also 2h, right? Sorry, h was half, so I think I made a mistake here. Yeah, h was distance between two dislocations, not I made it in. Yeah, so this is h. So this is 2h and this is 2h, okay? Don't go by the ratio in the figures. I think I have drawn it a little bit stretched in the vertical direction than in the horizontal, but like, yeah, just assume that they are all equal, okay? So, my dislocation density will be equal to, number of dislocations, that is equal to 2 divided by the area, 2h the whole square, right? Why number of dislocations is 2? Because in the center we have one dislocation, that is 1, and then at the corners we have 4 dislocations. So contribution of each dislocation at the corner would be 1/4. So 1/4 by 4 is 1. So 1 plus 1 is 2. So 2 divided by 2h square. That is equal to 1 by 2h square. That is my dislocation density. Okay. Or we can write h to be equal to, like if I'm rewriting this, h to be equal to 1 by root 2 into rho, root of 2 rho. Okay. So now if I want to rewrite my tau critical, that will be equal to GB by 8 pi 1 minus mu into h, or GB by 8 pi or tau naught, okay, or I can, let me just rewrite it here, GB by 8 pi 1 minus mu into root 2 rho, right? So if I just rewrite this as some alpha constant, all these constant values will take together. So then alpha GB times root of rho. This is my final relation, right? So this relation is known as Taylor-Harding relation. Okay. So this is my Taylor-Harding relation. Taylor's-Harding relation. Taylor or Taylor's? Is it? It's Taylor-Harding relation. Okay. So here, this tau naught represents shear strength of the material as a function of dislocation density. Okay. So this is essentially representing shear strength of the material as a function of dislocation density. Okay. Just a second. Yeah. So if we plot stress versus strain, okay, then we can understand this Taylor-Harding relation much better. So let's see how we can understand this from stress strain curve. Sigma versus epsilon. Okay. So this is my stress strain curve. Okay. Now what will happen if I load a material? Now here, initially my yield strength is here. This is my yield point, right? This is my yield point 1. So let's say this is y1. This is y1. So now if I load it till here, till this point, now when I unload it, what will happen? It will just come back parallel to the original line. And then again, if I load it, it will start, it will load plastically till this point. Let's say this was point A, this was point B. It will plastically load up to point B. Okay. And now my new yield point has become this y2, right? So essentially, we are seeing an increase in yield strength as we keep loading it more and more. So this is what the Taylor-Harding is saying. As we increase the load, there's an increase in the yield strength also. Okay. So we are seeing an increase in yield strength. Essentially, then also, what people have done is they have done experiments and they have plotted this B into root of rho. So root of dislocation density times Berger's vector versus tau normalized with G. Okay. So what they have seen is they have got a straight line for this. So essentially this also proves that this Taylor-Harding relation is actually correct. So we can actually get a relation between the shear strength that of the material as a function of the dislocation density. Okay. So how much is the influence of dislocation density on shear strength? We can directly get a relation. Okay. So this is about Taylor-Harding or how the Harding works. So now let's understand how these dislocations will multiply. Okay. Let's understand the mechanism behind this dislocation multiplication. So we'll have something known. We have to study something known as Frank-Reed mechanism. So I think you would have heard a mention of this in the previous class about Frank-Reed mechanism, but we'll study in detail about this mechanism. So let's assume that we have a dislocation like this, like one dislocation which is like this, which is moving in some direction due to the presence of some stress tau. Okay, some stress tau is being acted upon, and it hits some two pins. Okay, now these pins could be anything. It could be due to solute, precipitate, or it could be due to like dispersoids, or other dislocations, grain boundary, something. Some pin it is facing. Okay, there's two pins which are not allowing the dislocations to move forward anymore. Okay, so what will happen then? Now this dislocation will start bending around this pin, right? It will have something like this will happen. So this will happen. So as we keep applying load, or as the stress will kept on applying, then what will happen? Over time, the dislocations will go around the pin something like this. So they will start forming this kind of structure around the pin. Okay, and over time they will these 2 points will grow closer and closer. This point and this point and this point will come closer and closer. Okay. But what is one important thing to note here is these 2 points which are coming closer are having opposite signs of Burger's vector, right? So they will kind of annihilate each other and they will mix. So in the end, we will see a dislocation which is here at the center, but then another dislocation which is around it. Okay. So what essentially is happening is that as stress increases, dislocation density will also increase. And from Taylor hardening, we can say as dislocation density increases, and from Taylor hardening, we know that as dislocation density increases, the shear stress will also increase. Okay. Okay. Then what will happen is this dislocation pile up around one dislocation. So dislocation multiplying and all that, this pile up will lead to further strengthening. Okay. So now this dislocation pile up will lead to strengthening. So this is one mechanism by which dislocation multiplication can happen and then lead to pile up, which will lead to strengthening. Okay. So this is one mechanism. Now there are other mechanisms for dislocation multiplication as well. Okay, I think I'm having a lot of internet issues, but okay, I think I'm back now. Let me just check if recording and everything is working fine. Yeah, I think everything is working fine now. So let's continue. Okay. So yeah, I was talking about how there are other mechanisms for dislocation multiplication. So one of them could be due to accidents, for dislocation multiplication. Oh, sorry, in crystal growth from melt. So due to accidents in crystal growths leading to dislocation multiplication. So while crystal is growing, while there's crystal growth, that time also some accident might occur during the growth, okay? And that could be like due to presence of some other defect or something that can cause this accident, and that will result in dislocation multiplication. Next, homogeneous nucleation of dislocation, okay? The nucleation is non-homogeneous. If the nucleation is non-homogeneous, then we will see some sort of uh, like dislocation not getting formed easily, because then what will happen is the nucleation is not happening together. They are nucleating separately, and then what will happen is because of that the dislocations will not multiply very quickly. But if they are nucleating homogeneously, what will happen is they will multiply very quickly because they are nucleating together, and they are essentially aiding each other in nucleation. Okay, so that is why homogeneous nucleation of dislocation will also lead to dislocation multiplication. Then stress concentration, stress concentration at certain regions can also lead to dislocation multiplication. Stress concentrations. So this is also one of the most important factors for dislocation. Okay, just a second. Okay, stress concentration is another important way in which dislocation multiplication could happen. Okay, so these are about the different mechanisms for dislocation multiplication. Now let's move on to dislocation intersections. Okay, so what happens when dislocation intersect with each other? What are the different things that can happen? Okay. Okay. Now, two dislocations, they can intersect and leave behind jogs and kinks. Okay. Depending on how they're interacting or intersecting, they can leave behind some jogs or they can leave behind kinks. Okay. Uh, so as these extra segments that we are looking at, these extra segments, okay, they will require energy to form. Okay, because once they are intersecting, what will happen is you will need some amount of energy for these extra segments to be formed. Therefore, work done by external force is needed in order to like ensure this intersection happens. Okay, and therefore that will also result in hardening of the material. So as these extra segment require energy, Hence, work done by external force is also needed. So this will lead to hardening of materials. So how will this hardening happen? Essentially, we know this equation, right? E by L is equal to alpha Gp square, right? Now, what if this L is also equal to the Burgers vector? We'll see how this L will be equal to Burgers vector in a while. But just remember that what if this L is also equal to Burgers vector? Then in that scenario, the E becomes equal to alpha Gb cube, right? So this is the energy required for adding a step, either in the form of kink or job. So this is the energy required to add a step. Okay, this step could be in the form of kink or job. So one important thing that you have to note is that these steps that are formed in dislocation 1 will be parallel to Burgers vector of dislocation 2, and its size will be equal to the Burgers vector of dislocation 2. It's always that way. Steps formed in dislocation 1 will be parallel to Burgers vector of dislocation 2. Okay, and its size will be equal to the magnitude of Burgers vector of dislocation 2, and its size will be equal to the magnitude of Burgers vector of dislocation 2. Okay, so this is something that you can remember. But why? Why does this? Like, why do we say this? Like, can we actually see this and prove like this is actually the case? So let's take one of the cases, okay? Because we'll be studying 4 different cases now. Let's take the first case and you will understand very simply why this is the case, okay? Why we are saying that the steps will be parallel. The step formed in dislocation 1 will be parallel to the Burgers vector of dislocation 2, and its size will be equal to the magnitude of Burgers vector of dislocation 2. Why we are saying that? So we'll see that in the first case itself. We'll understand it. So let's say case 1. Okay. So in first case we'll examine two edge dislocations whose Burgers vector are perpendicular to each other. Okay. Two edge dislocations whose Burgers vector are perpendicular. Burgers vector are perpendicular. Okay. So this is So let's say we draw two dislocations on two different planes. Let's say this is one plane. Okay, let me draw the bottom plane first. Okay, and then we have the other plane. Okay, so we have one dislocation here. Let's say this is my dislocation line. Okay, and it has Burgers vector B1 in this direction. Okay, let me remove the arrow from the Burgers vector so that there's no confusion. Okay, so this is Burgers vector for dislocation 1. Now let's draw the second dislocation. So this will be my second dislocation. So its Burgers vector 2 is in this direction. Okay, so these are the two dislocations. Now after they intersect, how will they look? If you think about it, how would they look? So once B1, the Burgers, so the dislocation with Burgers vector 1 will come down and intersect, and dislocation with Burgers vector 2 will intersect. So they basically both cut each other. Then let's just redraw this part. Okay, so this is how the new dislocation would look like. At this point where it intersects, it will go down and then it will come like this. And by what magnitude will it go down? What would be the magnitude? This will be equal to this dislocation Burger vector, right? This dislocation. So this same magnitude, whatever is the Burgers vector of this dislocation, same magnitude you will see here also. Okay, so your S2 that you see here will be having the same magnitude as B1. Okay, so essentially, let me just add a few pages. Essentially, S2 will be perpendicular to B2. Okay, and S1 will be perpendicular to B1. Also, S2 will have the same magnitude as B1, while S1 will have the same magnitude as B2. Okay, these are things that will happen. Why? Because as you can see, the dislocation 1 is like cutting dislocation 2 and moving it in a way that now the step that is created in dislocation 2 is having the same size that dislocation 1 has pushed it by. And how much can dislocation 1 push it by? By the Burgers vector. So that's why S2 will have the same magnitude as B1. Okay. So you can see from the figure itself, you can see like what is the value. So essentially what you are having is you will see formation of jogs, right? Because these are all jogs. So you will have jogs which are formed having edge character, right? These dislocations will have edge character. and they will aid in glide. Aid in glide. Right? So they are glycine. Okay, they will aid in glide. So now let's move to case number 2, where there are two edge dislocations which are having parallel Burgers vector. With parallel Burgers vector. Okay. So again, let's draw the same thing, same two dislocations. Okay, but now the plane will be the other way around. So we have one plane like this, like last time. And the other plane, which will be like this. Okay. So you have one dislocation with Burgers vector B1 like this. B1, and another dislocation with Burgers vector B2. Both are in the same direction. Okay. So now what will happen when they intersect each other? Let me just actually see if I can copy this. Yeah, I can. Very interesting. I could copy and paste the whole thing. Yeah, okay. I just need to rub these portions off. Okay, so let's just draw the new dislocation. So first this B2 will draw. Okay, use green pen. So this is B2, and then for B1 we'll have ink. So both will have the same line of okay. So B2 and B1. Now S1 and S2 that are formed. This is my S1 and this is S2. They are kings, right? So the S1 and S2 are kings having screw character, right? Right? S1 and S2 are kings having screw character. What else can we say? Do they aid in glide or are they not aiding in glide? Both are aiding in glide, right? Because once the dislocation breaks, it's breaking in the direction that the motion is happening. So it can move easily once it has broken and move separately, and then the second half can move. So it can be like broken dislocation, so it will be easier for us to move it. Okay, but it is broken in the direction of motion, so it is easy for us to move. So both are aiding in length. Okay, so let's move on to case 3, where edge dislocation and screw dislocation are interacting. Okay. Edge and screw dislocation. So here we will draw the plane like this. So let's say we have a plane here. Okay, now this plane is broken something like this. Due to the screw. Okay, so we have a screw dislocation somewhere here, which is causing a net breakdown of the plane. Okay, and then we have an edge dislocation. See the different thing just to keep it clear. Okay, having Burgers vector B1 moving in this direction. Okay, so here Burgers vector is B2 in this direction. Okay, screw. So this is edge and this is screw. So let's write this as E and this one S. Okay. So what will happen once they interact? Now the entire the edge dislocation. Okay, let me just redraw this part so that we can. So now the edge dislocation also gets broken, right? So this is my edge. Gets broken like this, sorry, in this direction, and then continues on. So it gets broken in this direction, right? So this is my S1 here. This is my edge dislocation. Okay, having Burgers vector B1 in this direction. Okay, so this results in the formation of a jog here, which has an edge character, right? But what happens to a screw, which is having a B2 Burgers vector? So this B2 screw now, because of this interaction, this entire region, right? This thing breaks off like this. Okay, this interaction, and now the screw dislocation moves with the edge dislocation. The bottom half moves like this. Okay. Now this is my S2 here, and this S2 is also a jog, but it has edge character, which is not in the direction of the previous like Burgers vector. So initially we had Burgers vector B2. Now this S2 is not in the direction of B2. Now the problem with that is that this does not aid the screw dislocation motion. So this entire region gets blocked. So if I shade this region, this entire region will now get blocked. Okay. So essentially, here we are seeing S1 equal to B2 like always, while S2 is equal to B1 again like always. S1 and B2 are parallel again like always, and S2 is parallel to B1, right? So the first one, the S1 slip that we are seeing due to this in like S1 in dislocation 1 is glycine in nature, or it aids in what? Movement, right? Or aids in glide, while S2 is sessile and does not aid in glide. Okay, I hope that's clear. So now let's move on to the final case where we have two screw dislocations. Okay, so case 4, two screw dislocations. Just a second. Okay, so coming back to the two screw dislocation. So this is the last case. Just like previously, we will first be using this, okay, and then let's just draw the two screw dislocations. So we have one like this with Burgers vector 2 in this direction, and another one like this, okay, with Burgers vector 1. Okay, so these are the two screw dislocations. Now what are we understanding from here? Again, like if we move, the new screw dislocations will look something like this. I'll just draw it right here itself, the dotted lines, so that we don't have to. So the new screw dislocation will look something like this. I'll just put B2 here. Okay, while the new edge will look like this. The new screw, the B1 will look like this. Just draw this. So this will be B1. Okay. Okay. So I've drawn both of them in the same figure. I hope you can understand. Okay. So what is happening? Now, for the first time, we are not seeing just jog or just kink, right? We are seeing S1, which is parallel to B2 or equal to B2 and parallel to B2. Okay. And S2, which is equal to B1 and parallel to B1. Sorry, why am I right drawing perpendicular? I hope I didn't draw perpendicular somewhere else. Yeah, it's correct. Okay. Now, what is this S1? Is it a jog or a kink? S1 is a jog, right? While S2 is a kink. So S1 has, both of them have edge character only. Both of them have edge character only. But one is jog, one is kink. Now the jog essentially is sessile. If you look carefully, what is happening here? That jog is not helping it move in that particular direction, right? Because the Burgers vector is oriented in one way, while this edge is oriented in some other way, right? While kink is actually glissile. Okay. So now, if we look at all the cases, we have case 1 where we had jog. For dislocation 1, we had jog formation, which has edge character, which was glissile. While in case 2, we had two kinks being formed, both having screw characters, both being glissile, right? While in case 3, where we have screw dislocations, we have two jogs. Okay, so essentially, if you have one edge and one screw dislocation, you will have jog having both edge characteristics, but one of them was glissile and one was sessile. And in the fourth case also, you have two screw dislocations. So you had one jog and one kink formation. One of them was sessile and one was so jog was sessile and the kink was glissile. Okay. So essentially, there are three things that we can notice or we can write down. Edge dislocation gives rise to glissile steps that can aid in motion. Okay. So edge dislocation interactions gives rise to glissile steps. that can aid in motion. Okay. While screw dislocation, in screw dislocation, the step that is formed in screw dislocation, if it has jog characteristics, it will be H. Sorry, if it is jog, it will be H characteristics and will be sessile. While if it is kink, again it will have only H characteristics. So in screw dislocation, you will see only H characteristics. And it will be glissile. Okay. And finally, in H dislocations, we will have jogs, always jogs which are formed, which are having H characteristics, and kinks which are formed, which are having screw characteristics. Okay. In H dislocation, we will have jogs always having H characteristics, and kinks always having screw characteristics. Okay. So this much we have seen. Okay. Second. So now let's talk about one more important concept called dislocation locks. Okay. So we'll not go deep into it, just understand it from the basic perspective. Now, what happens when dislocations start interacting and start piling up, start opposing each other's motion and do not allow free movement? At some points, what will happen is some dislocations will go and sit in some place where it cannot move further. Okay. So if that happens, the dislocation is said to be locked position. Okay. Now in that scenario, what will happen is the dislocation will not allow any other dislocation to pass through and will not be able to move itself due to the influence of any other dislocation. Okay. Essentially, this lock happens when dislocations interact in a manner to create a new dislocation having Berger's vector which does not allow its motion. Okay. Moreover, they will not allow any other dislocation also to pass through. So essentially, this is like a dislocation lock. Does not allow any dislocation to pass through and does not pass itself. Okay. So this is one more important thing that we can remember. So last concept that we'll talk about is strain aging. Just quickly wrap this up. So if we are seeing a steel's stress versus strain curve, what we'll see is initially we'll see some raise and then some this kind of thing and then again like this, right? So this yield stress, higher yield point, lower yield point, etc. we'll see, right? We'll observe that. Okay. So now if we heat it to some level, let's say I heat it, let me just move this a little bit clearer. Let's say I heat it and I reach this point. Okay. And then I cool it down. What will happen? It will just go back here, right? And now when I heat it, if I apply load till this point A, and I leave it, it will go back down to point B, right? Then again, if I apply load, it will come back here and move in this direction only, right? Same direction it will follow. So this phenomena happens because the yield point has been reached and we have crossed that yield point, right? So without heating, we'll see this kind of phenomena happening. But supposedly we decide to heat it, okay? Supposedly, instead of letting it load and unload in this manner, we decide to heat it. Now what will happen is, this will go forward, again create that yield kind of phenomena, and again have this kind of thing. So after heating, you will see this kind of phenomena. And this is known as strain aging. Okay? So yield point phenomena, essentially what is happening is, yield point phenomena reappears. Reappears due to heating. Okay. So why does it happen? Because the solute atoms, they will diffuse to the dislocation location, and again they will not allow dislocation to move freely. Initially what happens when that yield point is reached, that dislocation is not able to move freely, right? But once we have moved beyond that, then that atmosphere is broken down. So now solute atoms will again diffuse into that dislocation locations, and again it will not allow dislocations to move easily and yield to happen again. Okay. So essentially you can say it happens because solute atoms they will diffuse to the dislocation core. When you heat it, solute atoms will diffuse to the dislocation core. Okay, so again you will have the reappearance of yield phenomena. Okay, so with this we come to the end of the theory part. Now let's move on to the problems. Okay, the first question: in an FCC metal, a pure edge dislocation D1 with a Burgers vector B1, which is equal to A by 2 1 bar 0 on 1 bar 1 plane, intersects. Just a second. Screen issue. Okay. Intersects with a pure edge dislocation D2 having Burgers vector B2 A by 2 1 bar 0 on 1 plane. The following are true, assuming steps are created are S1 and S2 and D1 and on D1 and D2 respectively. Okay. So what we are seeing, pure edge dislocation interacting with another edge dislocation, having what? Burgers vector, which are parallel, right? Or is it perpendicular? Are they parallel or perpendicular? Burgers vector are parallel, right? So which case would be true? You will see formation of jogs or kinks. We know that we will see formation of kinks, right? And kinks will have what character? Screw character. So which option says that? First one no, second one no, third one no, fourth one. So that is the correct answer. Okay, second question, match the following column. Solid solution strengthening. So what does solid solution strengthening lead to? It leads to elastic interaction between solute and dislocation. So we can match this, right? Strain hardening. Strain hardening will lead to what? Lomer-Cottrell barrier. Okay. Then grain size strengthening will lead to dislocation pile up at the grain boundary. And dispersion strengthening will lead to incoherency between dispersoids and matrix. So one is 2, 2 is 4, 1 is 2, 2 is 4. So this one is the correct option. 3 is 1 and 4 is 3. So this is the correct. Third question. The 3 stages of deformation in single crystals are characterized by. So single crystals, we have already seen there are three stages. One is easy glide, strain hardening, and dynamical recovery, right? So that is the first option. Okay. Now fourth question is a problem. Compute the dislocation density rho for copper crystal if it is deformed under a shear stress of 42 megapascals. Assume Taylor hardening, where G is equal to 50 GPa and Poisson's ratio is 0.5. Lattice parameter is given as 3.621. Okay. So we know that copper is a FCC material, right? Cu is an FCC material. So we have for FCC, B will be equal to A by 2. The Burgers vector will be equal to A by 2, 1, 1, 0. Right? Or magnitude of Burgers vector will be equal to A by root. Right? So my equation that I have is tau equal to GB by 8 pi 1 minus lambda times root 2 into dislocation density. Or I can write dislocation density to be equal to tau 8 pi, right, into 1 minus mu divided by GB times root 2 the whole square, right? So let me substitute and calculate the final answer. Please give me a second. So final answer I'm getting is 8.5 into 10 power 14 per meter square. So the closest value is this one. So that is the answer. Okay, let me just check 1 second. Okay, so this is the right answer. And then coming to the next question. Okay. So they have told the slip plane for the dislocation formed via Lomer-Cottrell barrier formed by combination of dislocation with Burgers vector A by 2 1 bar 0 1 on 1 1 1 plane with another dislocation having Burgers vector A by 2 0 1 bar 1 bar on 1 1 1 bar is what? Okay. So how do we do this? Very simple steps we have to follow. Okay. First is the few things we have to understand. If there is a Lomer-Cottrell barrier, okay, or any such dislocation lock, what is happening? Two dislocations are coming and they're locking each other, right? So essentially, the Burgers vector, first thing first, the Burgers vector are getting added up. Okay, so the new Burgers vector BR will be equal to B1 plus B2. Okay, so that will be A by 2 1 bar 0 1 plus A by 2 0 1 bar 1 bar. Okay. First step, always do this. So you will have A by 2, 1 bar, 1 bar, 0. So that's my Burgers vector. That's the first step. Second step is, now we have to identify where they both will come and intersect. Now, how do we know that where they will go and intersect? Now understand that these two dislocations lie on two different planes, right? So the only place where they both can intersect, essentially intersect, can happen only where both the planes are meeting, right? So they can intersect only when both the planes are intersecting. So both the planes, if this is one plane, let's say this is one plane, and this is my other plane. Now where are they intersecting? They are intersecting at some line here, right? So there will be a dislocation, there will be a line where these dislocations will intersect. So this line you have to identify. So let's say that line UR is equal to intersection of these two planes, right? So they will be, this line would be perpendicular to both the perpendiculars of these planes, right? So if the first plane normal is 1 1 1, second plane normal is 1 1 bar 1, so this will be perpendicular to both of them. So cross product of both of them will give me the plane. Okay, so let's do the cross product. So I'm getting 2 bar 2 0. Okay. So this is where the line would line where they both will intersect will exist. So finally we want to find the slip plane. So therefore the slip plane, where would the slip plane exist? It will be at the, and it will be perpendicular to both the Burgers vector as well as the line where the two dislocations are intersecting. So it will be UR cross BR, right? If we find their cross product, then we can get the final answer. Let me do that. So I'm getting 0 0 2. So this is the slip line. this is my 5 marks. Okay, so this is how you can solve a problem. First you add the Burgers vector, then you find the line at which these two dislocations will intersect. That can be found by taking the perpendiculars of both the plane or plane normals essentially, and then finding the cross product, as the dislocation line will be perpendicular to both of these plane normals. Okay, so once you know that, then slip plane would just be the cross product of these two lines, the Burger vector and the dislocation line. So it will be cross product of dislocation line times the Burger vector. Okay, so with this we will come to an end for today's discussion. I hope you have all understood how strain hardening works, essentially all the strengthening mechanisms we have gone through till now. I hope you have understood and caught up on all the strengthening mechanisms we have covered. In any case, if there are any doubts, we can discuss that in the next session. And so we'll end today's session here. I thank everyone for attending, and we look forward to meeting again in the next class. Thank you.